Hello students, this is our lecture number 10, solid state physics, unit number 1. Today we are going to study about the diamond structure. Okay, diamond structure is made up of carbon atoms which are bonded by strong covalent bonds. Okay, basically the diamond structure is nothing but the cubic lattice, okay, face centered cubic, which consists of 8 corner atoms, okay, and 6 atoms are at the center of the faces. Okay, we know that the cube has 6 faces, left and right, top and bottom, front and back. 6 atoms are present at the center of each face. Okay, so this is FCC. In addition to that, 4 atoms are placed inside this unit cell along the diagonal. Okay, now we will see how those 4 atoms are placed inside this unit cell, okay, to make diamond cubic structure. Okay, so first of all I will construct 4 diagonals. Suppose these are, I have labeled these 4 atoms as atom number 1, atom number 2, atom number 3 and atom number 4 in this bottom layer. Okay, now how many diagonals can be constructed? Okay, how many diagonals can be constructed with the help of this cubic? Okay, we know that the cube has 8 corners. Okay, by joining 2 corners we can construct 4 diagonals inside the unit cell of this face centered cubic. So for sake of easiness, I have labeled these 4 atoms as atom number 1, 2 and 3 in the bottom layer. Okay, now I will construct 4 diagonals inside this unit cell. So how to construct them? Okay, first this corner atom, okay, atom number 1 is joined with this corner. Okay, this is one of the diagonal. Okay, next with the help of atom number 2 I have joined this corner atom and that back corner atom. So this is diagonal number 2, and third diagonal I have joined this 4th atom to this atom. This is third diagonal, and fourth diagonal I have joined this third atom to that. So with the help of 8 corners, okay, we can construct 4 diagonals. So only 4 diagonals can be constructed within this face centered cubic unit cell. Okay, so in diamond structure there are 8 atoms at the corner, 6 at the faces of the centers, and 4 diagonals we will place along the 4 atoms we will place along the diagonals. So those 4 atoms are present inside the unit cell along the diagonal. Okay, so how can we place those 4 atoms? Okay, first of all, see this first diagonal with this purple color. This first diagonal I will place one atom which is at a distance 1/4 along this first diagonal. This atom, this green atom, I have placed 1/4 distance of this diagonal. Okay, again I am showing that this is the diagonal. Okay, and this one is the half of the distance of the diagonal, and this would be 1/4 distance. So one atom is placed at 1/4 distance of this first diagonal. Okay, now second atom is placed 3/4 distance of this second diagonal. So second diagonal starts from this second atom and ends on this atom. Okay, so second atom will be placed 3/4. Okay, this is the 3/4 distance of second diagonal, because second diagonal starts from this and ends on this. Okay, this is half of the distance of second diagonal, and this would be 3/4 distance. So second atom is placed 3/4 distance of second diagonal. Okay, now this one suppose third diagonal. Okay, so third atom will be placed at 1/4 distance, with respect to this third diagonal, because if you say this third diagonal starts from here and ends on this atom. Okay, so half distance will be this one, and this one is 1/4 distance. So third atom is placed 1/4 distance of third diagonal, and fourth atom is placed 3/4 distance of fourth diagonal. Fourth diagonal starts from this atom and ends on this atom, and 3/4 distance, this is half distance. okay, from this one to this is half, and this will be a 3/4 distance. So fourth atom will be placed 3/4 distance of 4 diagonals. So those four atoms are placed alternately at 1/4 and 3/4 distance of particular diagonals. Okay, so this is the diamond cubic structure. So diamond structure consists of 8 corner atoms, 6 face centered atoms, and 4 atoms, okay, alternately placed at 1/4 and 3/4 distance of diagonal. And those 4 atoms, okay, I have shown in green colors, and they are present along the diagonal inside this unit cell. So this is diamond structure, and this is also called diamond cubic structure. Now we will see the coordination. We will see the coordination number or coordination of the carbon atoms or coordination of atoms in this diamond cubic structure. Okay, so this is the one atom. This is the one atom in the inside the unit cell is coordinated by 4 other atoms. Okay, one atom at the corner and 3 face centered atoms. So the coordination of this green atom is 4. Okay, so this green atom is tetrahedrally coordinated by other 4 atoms. If suppose this is carbon atom, this carbon atom is tetrahedrally coordinated by 4 other carbon atoms. Similarly, this atom is also tetrahedrally coordinated, one at corner atoms, one coordination to the corner atoms, and 3 atoms are coordinated at the face centered atoms. Okay, so the coordination of this atom will be 4, tetrahedrally coordinated. Similarly, this atom is also tetrahedrally coordinated, one is at corner and 3 atoms are at the 3 atoms are nearby atoms which are at the center of the phases. So it is also tetrahedrally coordinated, and this atom is also tetrahedrally coordinated. Okay, so the atom present inside the unit cell along the diagonal is coordinated by 4 other nearest neighboring atoms. So hence its coordination number will be 4. Okay, so the coordination number for diamond structure or diamond cubic structure is 4. Okay, now this diamond structure can be represented two-dimensionally also. So how to represent this diamond structure or how to present this diamond structure two-dimensionally? Okay, for that I will consider the bottom layer. Okay, this is the bottom layer. Okay, now I will present this diamond cubic structure two-dimensionally. For that I am labeling this bottom layer atoms. Suppose this is 0, 0, 0, this is 0, and this is center atom, center of this phase atom, which are at the center of this bottom layer. So I have labeled these 5 atoms at 0th position. Okay, because I am drawing, okay, I will draw, or I am drawing this diamond structure. Okay, I will represent this diamond structure two-dimensionally. For that I have to consider one bottom layer. This is bottom layer, and these 4 atoms are present at the corner of bottom layer and one at the center. So I have labeled these atoms which are present at the bottom layer as 0th position. So they are at 0th position. Now above this bottom layer, which is exactly at the half of the height. If suppose I am considering the height from this bottom layer to top layer. Okay, this is top layer and this is bottom layer. So suppose exact height is 1. Okay, suppose again I am showing that this is bottom layer and this is top layer, and height between the bottom and top layer suppose 1. So this atom is present exactly at the height of 1/2 or half height from this bottom layer. Okay, so this atom is exactly at the distance half from the bottom layer. Okay, if I consider the distance from this point to this point is 1, so this will be half. Okay, half distance. Similarly, this face centered atom is also at the half distance from this edge. Okay, this face centered atom is also at half distance from this edge. Okay, and this center atom is also at the half distance from this edge. Okay, these bottom layer having this bottom layer is having 4 edges. So this atom is which is at present at the half distance from this edge, this atom is also from at half distance from this edge, this atom is also from half distance from this edge, and this atom is also present at the half distance from this edge. Okay, if I want to show these face centered atoms, okay, two dimensionally, so I have to show exactly at the center of each edge, okay, at half position. So bottom layer, just look, this is the bottom layer atoms at the 0th position, 0 0 0 0, and this center. So how can we show in two dimensionally? Okay, I will show in next slide. Okay, we will show 0 0 0 0 and 0 exactly bottom layer atoms at 0th position, and face centered atoms I will show here the center of each edge and at the position of half. Okay, and now we will show these four atoms inside the unit cell. Okay, two dimensional, how can show these four atoms which are present inside the unit cell along the diagonal? Okay, two dimensionally. For this I have to construct two diagonals in the bottom layer. Okay, by joining this and this atom and this atom, these are the two diagonals. Okay, two dimensionally in the bottom layer. Okay, and on this two diagonal I will show these four atoms. So how can we show? Suppose this is first atom. If I draw a perpendicular, so this perpendicular will intersect exactly at a distance of 1/4 on this diagonal, 1/4 distance from this corner. Okay, so I will place this atom here. Second, this atom, if I draw a perpendicular from this atom, it will intersect this diagonal, and this is at 3/4 distance from this corner, 3/4 distance, because this atom is present 3/4 distance of the diagonal. So I will label as 3/4. Similarly, if I draw a perpendicular from this atom, so it will intersect exactly 1/4 distance, because this diagonal atom is present at the 1/4 distance. Okay, I have shown in last slide, previous slide. Okay, similarly, if I draw a perpendicular from this atom, this will intersect at 3/4 distance, because this atom is present at 3/4 distance along the diagonal. If it will intersect here at 3/4 distance. So this bottom layer, so all the atoms I can show in this bottom layer two dimensionally. If I draw a bottom layer in square shape, these are the four atoms of the bottom layer, and one is center atom which are at 0th position. Just look at this three-dimensional structure. I am going to show this three-dimensional structure in two dimensionally. So for that I will have to show first bottom layer. So these are the four corner atoms and one center atom of the bottom layer which are at 0th position. So I am showing this. Suppose this is bottom layer and these atoms are at 0th position, one is at center. And face center atoms, these are the face center atom which is present as exactly at the center of each edge. There are four edges at the bottom layer which are at half position. So these are the face center atom which are at half position, and along these are two diagonals, 1 and 2. One atom, these are at diagonal 1/4, this is 3/4, this is 1/4, and this is 3/4 distance. Similarly, that I have already shown in this three dimensional figure. Say this is the bottom layer. Here I have to place one atom as 1/4. Here is 1/4. Here is 3/4, and here is 3/4. So these three-dimensional diamond structure I can show two-dimensionally in this way. This 1, 2, 3, 4 corner and one center atom at the bottom layer atoms which are at 0th position. These half are face-centered atoms which are at half height from the bottom layer, and these are the atoms which are at distance 1/4 and 3/4 alternately. Okay, 1/4, 3/4, 1/4, 3/4. Okay, so this is the two-dimensional representation of diamond cubic structure. And if I see the coordination, and I already said that the coordination number, each carbon atom is tetrahedrally coordinated, so the coordination number would be 4. If I want to calculate the number of lattice points per unit cell, you know that the contribution of corner atom is 1/8, contribution of face centered atom is half. Okay, half of contribution of face centered atom is half, and 4 atoms are inside the unit cell. So total number of atoms per unit cell, there are 8 corner atoms. Contribution of each corner atom is 1 by 8. 1 by 8 into 8, plus there are 6 face centered atom. Contribution of each face centered atom is half, plus 4 atoms present inside the unit cell. Again I am showing that. Just look at this structure. There are 8 atoms. These red atoms are present at the center, at the corners of unit cell. So there are 8 atoms. Each one atom is having 1 by 8 contribution. There are 6 face centered atom, which I have shown in white color. Okay, and there are 4 atoms present inside the unit cell, which I have shown in green color. So how many atoms? If I count that, 8 atoms at the corner, 6 at the face center, and 4 at the inside the unit cell. So total 8 plus 6 14 plus 4 18. Okay, but the contribution of corner atom is 1 by 8. Contribution of face centered atom is half, and 4 atoms are inside the unit cell. They give full contribution. So number of atoms per unit cell will be calculated as 8 number of corner atom. Each atom has contribution 1 by 8. 1 by 8 into 8, plus 6 face centered atom. Each atom is having contribution 1 by 2. Half into 6, plus 4 atoms inside the unit cell. So total, if I calculate these, 8 cancel, 1 plus 2 1s are 2 3s are plus 4. So there are 8 number of atoms per unit cell, and we know that the contribution of corner atoms 1 by 8, contribution of face center half, and number of atoms inside the unit cell 4. So total number of atoms per unit cell for this diamond structure will be 8. Okay, now we have seen the diamond structure 3-dimensionally and how to put the atoms along the diagonal which are present inside the unit cell, and we have also calculated the coordination number, and we have also calculated number of atoms per unit cell. Okay, now we will see how to establish the relation between radius of atom and side of the unit cell. You know that the diamond structure is cubic structure, so all sides of the unit cell are equal. If suppose A is the side of A equal to B equal to C, all sides of the unit cell is equal. All sides of unit cell is equal. So suppose this is diamond structure. Okay, suppose this is the diamond structure. We have seen the diamond structure consists of 8 atoms at the corner, 6 at the face center, and 4 inside the unit cell. Now we will see how to establish the relation between the radius of atom and side of the unit cell. Suppose this atom is O atom, A atom, B and C. I have labeled the position of these atoms O, A, B and C, and suppose these atom at the position P. I have labeled these 5 atoms O, A, B, C, and this one is P. Okay, now if suppose this, and you know that the edge of unit cell or side of unit cell or side of diamond structure is A, because all sides are equal, because it is a cubic structure A. Okay, now suppose it is a diagonal, is joined from O to B atom. This is the diagonal. If I want to calculate the length of this diagonal OB, okay, this is a 90-degree angle, okay, and this is right angle triangle. If I want to calculate the length OB, length of diagonal OB, and we know OA and AB, so this is right angle triangle. So with the help of Pythagoras theorem in triangle AOB or OAB, OB means diagonal, OB square is equal to OA square plus AB square according to the Pythagoras theorem. OA is nothing but A, AB is nothing but A square plus A square, so twice A square. Okay, so OB will be, so the length of diagonal OB will be under root twice A. Okay, now if suppose I join this O and C atoms, another diagonal, this is another diagonal O and C, and this is another right angle triangle. Which right angle triangle? OBC. OBC is the right angle triangle, and I know the length of OB and BC. BC the side of the unit cell A, and OB is the first diagonal, that's length is root 2A. Now I can easily find out OC. This is also a right angle triangle. So in right angle triangle OBC, Okay, OC is the diagonal, so OC square is equal to OB square plus BC square according to the Pythagoras theorem. But the length of OB is under root 2a plus length of CB is a under root 2a square plus a square, that is 3a square. So OC will be root 3a. OC will be root 3a. Okay, so I have found out the OC. OC will be root 3a. Now we know that this is the diagonal, starts from O and ends on C, and this P atom is present inside the unit cell, which is at distance 3/4 from point O. P is present at the distance 3/4 from point O, but it is present at the distance 1/4 from point C. So C से यहाँ तक, from C to P, the distance is almost 1/4 of the diagonal, and we know the the length of the diagonal OC is nothing but root 3a. So what is the length between PC? Because P is at 1/4 distance of this diagonal, so P will be under root 3 into a divided by 4. So length of PC is under root 3a divided by 4, because P is present 1/4 distance from C atom. So this P and C atoms are joined together. These P and C atoms are close to each other, such that their boundaries of atoms are coinciding. Okay, this atom P and C are close together. Okay, just look at this. P atom is present at the distance root 3/4 from root 3/4 of this diagonal. So the distance between CP is nothing but root 3/4 into A. Okay, now look at this. This C and P atoms are placed very close to each other, such that their boundaries are coinciding. So the distance between the atoms C and P, okay, यहाँ तो ऐसे C and P atoms दूर दूर दिख रहे हैं, but C और P atoms closely placed है together, बहुत एक दूसरे से जुड़े हुए. So the their radius are joined together. So distance between the atoms C and P is nothing but R plus R, twice R. Distance between C and P is nothing but the twice R, but the CP is nothing but what? CP is nothing but root 3/4a, because the P is at distance 1/4 from the point C. Okay, 1/4 means the diagonal distance of 1/4. The diagonal distance is root 3 into a. So the distance between CP will be root 3 into a divided by 4, because this is at 1/4 distance from C. Okay, from C means it is the distance at 1/4 of this diagonal. So diagonal length is root 3 by a. So the distance between C and P will be root 3 by a divided by 4, because this is at 1/4 distance from C. So but CP is twice R, so I will get, thus twice R is nothing but root 3/4 into a, and from here 2 will go to that side. I will get R is equal to root 3/8 into a. Okay, now we will get the relation between the radius of atom and side of the unit cell. So it will be R is equal to root 3/8 into a. So with the help of this radius, the relation between a, side of the unit cell, and radius, we will easily find out the packing fraction. Okay, so what is packing fraction? We can easily find out the packing fraction for diamond structure. So what is the packing fraction or packing density of the diamond? Number of atoms per unit cell into volume of each atom divided by volume of unit cell. So number of atoms per unit cell means number of atoms per unit cell for the diamond structure is 8 into volume of each atom. Atom is spherical shape, so the volume is 4/3 pi r cube. Volume of unit cell, the side of unit cell is A equal to B equal to C, A, so volume of unit cell would be A cube. So 8 into 4/3 into pi, but R is nothing but root 3 A divided by 8. Just I have established the relation. R is root 3/8 divided into A. So in place of R, I can put root 3 into A divided by 8 cube divided by A cube. Okay, now we will calculate it. Okay, so this will be root 3 cube, that is 3 root 3 A cube. Okay, and this is 8 cube. So here is what 8 can be cancelled out, so it will be 64. Okay, 8 cube, 1 8 in denominator, 1 8 in numerator, cancel out, so only 8 square will remain, so 8 square means 64 divided by a cube. Now we will calculate it, 4 by 3, this is root 3, okay, root 3, 4 root 3 pi, okay, these 3 and this 3 will be cancel out, okay, again I am showing that, again I am showing, okay, these, okay, again I am showing this one, this a cube cancel out, and this 3 and this 3 cancel out, so we will remain with 4 into root 3 into pi divided by 64. So 4 ones are 4, 4 16 are 64, so I will get root 3 pi divided by 16, and the value of root 3 is 1.732, pi value 3.142 divided by 16, so I will get the answer of 0.3401. So packing fraction will be 0.3401. If I multiply this by 100, so I will get percentage packing density or percentage packing fraction, that will be a 34%. So for diamond structure, percentage packing fraction will be 34%. So today we have studied how to construct a diamond structure, okay, how to extract the structural parameters from it, okay, and how to calculate the packing density or packing fraction for the diamond structure. So it's all about the today's lecture, okay. So in next lecture we will see about the zinc blende structure. Thank you.